Hello, this is Dr. McNeil again, and welcome to part two of our lecture on Chapter 2, Describing Data Using Distributions and Graphs. Hopefully you've had a chance already to watch part one of this lecture, and my hope is that my lecture added to your reading of the material fosters a deep understanding of the knowledge base that we're creating in terms of our first task, which is really to understand descriptive statistics as we head into the later part of the class where we will focus on inferential statistics. So today's lecture will pick up where part one left off, meaning I highlighted the following key terms. I always start off by focusing your attention on the key terms of each chapter. And the reason why is this concept. Well, most people have a little bit of statistics anxiety or math anxiety. There is some math, as I mentioned, in statistics, but it's not a lot of math. It is simple math, but it can sometimes get a little complex, not very complicated. So let's focus and let me remind you of the three key terms that I highlighted in part one. The three terms were box plots, frequency polygons, and stem and leaf display. I want to remind you that of the three, box plot, frequency polygons, and stem and leaf display, I've already shown you frequency polygons. Take a quick look to remind yourself of that brief introduction of this type of graph. Okay, so far we've looked at several graphs. We looked at a table graph, frequency graph, we've looked at a pie chart, we've looked at a bar chart. Now let's take a look at a line graph. If you take a look at this line graph, I'll give you a second to just sort of take it in. See if you can use or leverage the idea that I just shared with you a minute ago, that a picture is worth 1,000 words. If that's true, what words do the story of this picture tell? Okay, so now let's take a look at the other two, box plots and stem and leaf. Look at box plots. And what you see here is figure 2.8 is a data set that has the number of touchdown passes in a season of all the football leagues within the National Association. On the other side, you have what's called a stem and leaf chart or a stem and leaf graph. Here you can see on the left side of the graph, it's called the stem, and it starts with number 0 and goes up to 3. And that sort of corresponds to the data over here, meaning the stem is the first decimal point, and so it would go from 0 to any touchdowns of 30 or more. And so how this is arranged is you have a stem on one side and you have the leaves on the other side. First, I'd like you to take notice that the data set is arranged chronologically. So you have 37 at one end, which is the highest, and 6 at the lowest. And how that data set can be translated or converted to a stem and leaf looks like this. So we started with our first data set, our lowest, which is 6. 6 is represented here on the line with 0, and that represents the 6. Here represents the 9. Those are on the 0 row to indicate the tens column is 0. Then when we get to stem 1, this represents 10 to 19. So we can see that we have two 12s, and the two 12s are represented here. This first 2 is a 12. The second 2 is a 12. Hopefully you can see that. We have 3 14s, and we have 3 4s here. This first 4 represents, because it's on the line with 1, represents 14, 14, 14, 14. So it's easy to see how you can convert a data set, a simple data set, from a group of numbers to a stem and leaf graph, which gives you some sense of its shape. And what I mean by giving you some sense of its shape is if you tilt your head to the right, doesn't look great on camera, but if you tilt your head to the right, you should see that there are sort of four peaks, and the peak where for the stem number one is the highest peak, stem number two is one less than. So you get a sense of the shape of the data, and that's really the value of stem and leaf graphs. But stem and leaf graphs can be as simple as this one or as complicated as you're about to see next. So if you take a look here, we have the exact same data from before, from figure 2.8 or 2.9 that we just saw on the previous slide. But the difference is you can see that the stems, the numbers on the left, have been separated, or they're stacked in twos. And what that means is this first zero obviously means zero, but this first one is 10 to 14. So any number between 10 and 14 would go on that line. The second one, however, goes from 15 to 19. The first two goes from 20 to 24. The second two goes from 25 to 29, and the same for the next two threes. And in this way, if you recall, when I asked you to turn your head to the side, 1 and 2 were really tall columns. But now if you turn your head to the side, because we've broken each of the range of numbers, we've broken them into two columns or two rows. Now you can see that it has a little more of the shape, and you can tell that the highest or the most number of touchdowns is between 20 and 23. That's where most football teams scored in that season. But now if you take a look at figure 2.11, this is called a back-to-back stem and leaf. And all it's doing is using the same stem, but we have the stem in the middle, and you can see that the stem is broken into the same two levels or two tiers as I just showed you in figure 2.10. But we're seeing on one side, the left side, we're seeing the data for 1998 touchdown data. And on the right side, we're seeing data from the year 2000. And in this way, you can see, if you tilt your head to the left, you can see the data, the shape of the data for 1998. If you turn your head to the right, you get the shape of the data for 2000. You can see that the data for these 2 years is fairly similar, except there are some outliers, meaning in 1998, there were at least 2 teams that scored 41 touchdowns that season. The highest that occurred in 2000 was 37. So you can get to see that some of the data sort of clumps to the middle, some of it spreads out. You get to see how high it is. And you can see that here we have 41 and 37 sort of hanging out by themselves. We would call those outliers. Again, all we're seeing here is how the values are arranged in 2 tiers that allows you to see information a little bit clearer. Here we're seeing one side, 1998 versus 2000. But this gives you a sense of the flexibility and the dynamic use of stem and leaf charts. Again, particularly if the data set is not very large. And I would say that a data set gets too large at about, I would maybe say 50 numbers when you sort of lose track. And remember, before you can arrange a stem and leaf, you have to organize all the data in chronological order. So that can get very tricky unless you're using a computer to organize the data, much beyond 50 or so pieces of data in the data set. If you take a look at the data set in figure 2.12, I'll give you a second to really take a look at it, to take it in and see what's different about it than what we've seen in the previous 2 data sets. Did you see it? Do you see it? Here we have, for the first time, a data set that is continuous. In our previous data sets, they've all been discrete numbers, whole numbers. here you're seeing numbers that go into beyond the decimal point, that go out into actually infinity or ad infinitum. You can see that this data set presents priming. A lot of research that is performed is how quickly does a respondent or participant respond after receiving a particular stimuli. So we're seeing a range of response from participants from 43.2 seconds all the way to negative 27.4 seconds. Not sure what the study is, but you can see this range. Well, how can we take continuous data and convert it to a stem and leaf? If you take a look, you also will notice that we also have negative numbers. So a stem and leaf can not only show the shape of positive numbers, but it can also show the shape of negative numbers. But notice in the stem and leaf that we only have discrete integers. We don't really represent the continuous aspect of the number. So if we start at 43.2, which is the highest, actually in this case, it's the longest amount of time, 43 seconds, if we're counting how quickly someone responds. So 43.2 is actually represented in the stem and leaf as just 43. We round it down, 43.2, round it down to 43. But look what's happening with the next number, 42.9. 42.9, we also round, but this time we round up. So we have two 43s in the stem and leaf chart. Notice what happens when we get to the negatives. We can see here that negative is denoted by having 0 as the stem for the positive side and negative 0 as the stem for the negative side. But take a look at this first number here. So remind myself to turn on my pen. Take a look at this number here, negative 0.2. Where would you round that out? Well, it's a negative number, so it needs to be on the negative side. And 0.2 means we can't round it up to 1. We actually round it down to negative 0. Take a look here at negative 6.3. You can see 6.3 as negative 6. And negative 6.7 rounded up to negative 0.7. And hopefully you can see how that works. The brief chart of how we are dealing with the negative numbers. Negative 0.2 is rounded to negative 0, negative 6.3 is rounded to negative 6, negative 6.7 rounded to negative 7, and on and on. This should give you a good sense of how stem and leaf charts or graphs work. I hope that you take some time to really review this information. It will show up again, and give yourself an opportunity to practice. In fact, if I were you, I would take the data, the very first data from the football data set. I would try my hand at creating the stem and leaf graph myself. Now let's take a look at some other ways that we graph data, namely histograms. Here we're looking at data in this table 2.2. It's a grouped frequency distribution of psychology test scores. These data, or what you're seeing here, are 3 columns: the interval lower limit, the interval upper limit, and the class frequency. So to make this a little more plain, these are scores from 642 students on a psychology test. So if you added up all the class frequencies, here the sum would be 642. So scores from 642 students. The test consisted of 197 items, correct or incorrect. And so the highest number that you could get is 197, the lowest that you could get is 0. The scores of this data set actually ranged from 46 to 167. And so how it's arranged is through what we call bins. 46 is the score, is the lowest score, and it's sitting in a bin where the lower interval is 39.5 and the higher interval is 49.5. And there were three scores, or three students whose scores were between 39.5 and 49.5. And we can see all the way up, I said that the scores range from 46 to 167. There is a 167 here, just like we had a 46 here. And 167 is sitting in a bin where the lowest value is 159.5 and the highest value is 169.5. So you can see a little bit how the scores are distributed by simply looking. Well, we can tell very quickly that each bin is the size of 10 width. You can see that three students got the lowest scores between 39 and 49. One student got the highest score between 159 and 169, followed by another student who got between 149 and 159. But we wanted to see what's the mode, meaning the mode is a way of telling what number exists the most often. There are three means of central tendency: mean, medium, and mode. And mode is the number that exists the most. You'll see that 147 students got scores between 79 to 89. So that's the mode. And if we wanted to take a look at what the histogram looked like, this is what we're looking at it, how we're looking at it now in a frequency distribution. This is what it looks like as a graph. If you take a look, we can see exactly the same data that we were just looking at. This time it's in the form of graph. Remember that there were two students who scored the lowest, and also remember that the x-axis usually represents the categories, and the y-axis, or the vertical axis, usually represents the values. In this case, the y-axis still is, the x-axis really still is the category, and the category in this case are each bin. You can see that the bins go from 39.5 to 49.5, and they go to the 0.5 to make sure that no score is overlapped, that it can only go in one bin or another. If you recall, there were two students who had scores between 39 and 49, and we can see that's about two students right there. Recall that we had one student who had the highest score, that's one here between 159 and 169. Another student who got between 149 and 159. But now as you take a look at the graph, you can see how it's arranged, and you can see whether it is balanced or symmetrical, or you can see whether it is skewed, meaning is it skewed to one side or the other. An easy way to tell whether the data is normally distributed or symmetrical, or whether there is a skew, is to first find the highest peak. So here's the highest peak. And then count the bars to the left and count the bars to the right, or the left to the right, however it is for you. Moving to the left, 1, 2, 3, 4 bars to the left. Now let's move to the right of the peak. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it keeps going. So in this case, I think William asked that question earlier. In this case, we can see that this data is positively skewed, meaning it keeps going after the 4 on the left side, it keeps skewing positively. And so that's the difference between symmetrical or normal, or positive skew or negative skew. In this instance, we have positive skew. Recall that there were three graphs that I was going to show you: box plot, frequency polygons, and the third was stem and leaf. I've already shown you frequency polygons. I just showed you stem and leaf, and now I'm going to show you box plots. I saved the best for last. This one will require a little bit of math, so maybe get your calculator out. Remember, you can stop this video at any time, rewind it, look at it again. You can put the video on pause to work out the calculations yourself to confirm. I always think that the best way to learn is to do it yourself, even if the answers are there. It helps get some muscle memory. Okay, so let's take a look. Let's start first with the data set. Here we have a data set, figure 20 or 2.20. And this data set are times of women in, I believe it's a race. Let's say it's a race. All right, and so here are the times, or the places, is their placement. I believe that's what it is. It really doesn't matter what the data is, it's just that we have a set of data. We can see that the data ranges, it starts at 14 and it goes to 29. And we're going to take this data and arrange it so that we can see the quartiles. What is the 25th percentile, the 50th percentile, the 75th percentile? These are terms that we've heard a lot, particularly, I think that's often referred to when talking about a student's graduation status or graduation or class status. They are in the upper 2% and the upper 5%. This is the work that we're doing when we're talking about quartiles. So if you look here in figure 2.21, the first step, as it says here, of creating a box plot is to create what's called the interquartile. And the interquartile is the 25th, the 50th, and the 75th percentile. Here's a little brain teaser. If you had one loaf of bread and you were the eldest child and you had to serve your 3 siblings, and each one of them had to have an equal amount of the bread. So you need, including yourself, you're going to take this loaf of bread and to cut it into 4 equal pieces. How many slices would you make? Think about it. Most people think, I'm going to make 4 slices because I want 4 pieces of bread. Well, actually, if you have a whole and you're trying to divide it into 4 equal parts, you're actually only going to make 3 slices. And that's sort of essentially what's happening with graphing in box plots. So first, what we're going to see is that the interquartile is the 25th, the 50th, and the 75th percentile. So the 25th is always the bottom part of the box. The 50th is the line in the middle, and the 75th is the top line. So on the left side, we see the female times the 25th, 50th, and 75th percentile. And on the right side, we have the men's time. Again, we have the bottom line, which is the 25th, the lowest percentile, the 50th, which is in the middle, and the 75th. So looking at comparison side by side, female and male, but you can see that the 75th percentile for women is just higher than the lowest of the score in the 25th percentile for men. You can see where there's overlap and where there isn't any overlap. So you can see that the fastest woman is just a little bit faster than the slowest man. And you can also see where the percentiles are in terms of the 50th percentile. You can see here for the men, because the 50th percentile line is directly in the center of the interquartile, that suggests that this data is normally distributed or symmetrical, meaning it's going to fall evenly on both sides. If you take a look at the female, you can see that the 50th percentile is a little bit higher. It's not in the center. It's closer to the top, which again gives us the idea of skewness, that this would also be positively skewed. If that's not intuitive, wait for a bit, it may become a bit clearer. So the question then becomes, how do you create out of this data the 25th percentile, the 50th percentile, and the 75th percentile? It is a very simple formula. So first you start by sorting the data in order. So now we have the data. And to get the 25th percentile, which is the bottom, the formula is 0.25 times 31. And 31 represents the number in the data set. If you counted these numbers here, you would find that there are 31 of them. So it's 0.25 times 31, which is the data set, plus 1. That plus 1, we don't want to really get into that right now, but it's called an interpolar. It's just a way so that we can make sure that the percentiles don't fall into a continuous number. So the result of that formula, 0.25 times 32 essentially, which is 31 plus 1, equals 8. So the 25th percentile is the 8th value. So we look at the sorted data, 1, 2, 3, 4, 5, 6, 7, 8. It's the first, it's the next to the last 17. You take a look here, that's just about where the 25th percentile is. And it's a similar formula, except for the 50th percentile, instead of 0.25, it's 0.50 times 31, which is the number of the data set, plus 1, which is the interpolar, equals 16. So the 16th number in the ordered set is the 50th percentile. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16. 16, right? And that is, sometimes you have to sometimes make a decision. And here I counted 16, and the 16 number was 19, but it could have also been 18. When the numbers are so close as between 18 and 19, it's pretty negligible which number you choose. But here again is the same formula for the 75th percentile. Again, 0.75 instead of 0.25 or 0.50. Those are the percentiles, times the number in the data set plus 1 for the interloper, and we get 24. And that's exactly how we create box plots. We'll talk about this in a little bit greater detail, particularly how you can use box plots because they're very relevant to you. Box plots are how your grades are posted in Canvas. Instead of a vertical box plot, your box plots are horizontal, but they're really essentially communicating the same thing. The only thing that we're missing on this box plot are whiskers. We'll talk about that a little bit later. The whisker is the highest number and the lowest number. But essentially, you're looking at the box plot, which is the interquartile, which is 25th, 50th, and 75th percentile. Remember those 3 slices that you would make in that loaf of bread to make 4 equal parts. All right, let's wrap this up. We've taken a look at 3 different kinds of graphs. We took a look at stem and leaf, histogram, and we've taken a look at line graphs, which is the frequency polygon. Stem and leaf, they're useful for showing proportions and percentages and to see the shape of data. You can have the stem be a single number, or you could break it down so that you have stacks of 0 to 5, 0 to 4, and 5 to 9, so that you can, again, sort of flatten it out to see more of the shape of the data. You can also use back-to-back stem and leaves to see and to compare the shape, which allows you to see where the data is sort of clumping up and where there might be outliers. We took a look at histograms, where we're taking a look at data in bins or different buckets. And the buckets are designed so that each score can only be in one bucket. And the buckets allow you to see the shape of the data. This is also a way for us to be able to note whether the data is normally distributed or symmetrical, or if it's skewed, either positive or negative. Also, we looked at line graphs, which are very useful when you're trying to show change over time in either one series or 2 series, as we did with the card games, looking at the frequency of players of card games on Sunday or Saturday versus Wednesday. All right, that should do it. That should wrap up week 2 or chapter 2. where we took a look at how data is distributed or how it looks is represented in graphs. We have this week, as always, your discussion board. I'll be looking forward to your questions for your peers and the way that you're answering each other's questions. That will help you with the exercises. Make sure that you are doing the exercises, particularly that you are working through the exercises where the answers are given on the odd numbers. I always recommend that you complete the answers on your own and then go back and check. All right, so that should take care of chapter 2. If you have any questions, make sure that you bring them to the discussion board. And I'm looking forward to your participation and your performance in this week's quiz. Lastly, I want to remind you to be on the lookout for getting your calculator, the Texas TI calculator. I'm going to place that link in Canvas so that you can find it. It's about $9 on Amazon. But having said that, good luck this week, and I'm really looking forward to checking out all the statistics you find. Good job.